Alrighty, hey everyone, welcome to Cassandra Lunch number 88. Today's topic is going to be on Cadence, and we're going to discuss how Cadence can work on top of Cassandra to provide workflow management at scale, and Cadence architecture in the context of SAGA Patterns. Today's topic is going to be given by Rahul Singh, CEO here at Anant. Co-organizers for the event are Rahul and myself. If you are interested in giving a talk at Cassandra Lunch or our sister lunch, Data Engineers Lunch, feel free to reach out to me. My email is listed below. Additionally, if you're looking to sponsor or bring more members in, you can find all of our videos on youtube.com/AnantCorp. You can subscribe, and you can also reach out to us via that way. We are part of Data Community DC. Data Community DC believes in an inclusive culture, no matter your race, gender, sexual orientation. Everyone is welcome, and we respect that, and we expect that respect to be given to all. Data Community DC is built up of a bunch of different organizations. We are part of DATASTAX DC, but our sister lunch is a part of Data Wranglers DC. So if you are interested in all the different various events and organizations that fall under the umbrella of Data Community DC, you can find out more at datacommunitydc.org and all the various events that are listed by the various organizations. So what do we cover here? We cover everything that is, talks, or plays well with Cassandra, whether that be open source Cassandra, managed Cassandra like DataStax Enterprise, or other variants such as Skilla, Cosmos DB that's compliant, Amazon key spaces, as well as things that play well with Cassandra like Spark, Kafka, Airflow, and a bunch of other different technologies. So this is a time for, if anyone's new, they can drop a hello or hi in the chat. We'll go ahead and move on. Group roles, if you have a question, feel free to ask it. This is a community, so please do share what you know with us. But however, please keep in mind the speaker's preferences in terms of receiving questions or comments during their presentation. So if you have a question, you can drop it in the chat, or the speaker generally goes over their preferences at the beginning of the presentation. Here at Anant, we design, build, and manage global real-time and data analytics platforms surrounding Cassandra, Spark, and Kafka. So Cassandra's our bread and butter, so we love to be part of the community and have people talk about Cassandra. DataStax is a partner and a sponsor. GW University is also a sponsor for having in-person events. They provide venue space. We also have some institutional and organizational sponsors. Any announcements anyone has in the audience, you can drop it in the Zoom chat here, any jobs, meetups, hackathons, etc. You can also drop it in the YouTube chat if you're watching it on YouTube currently. One of the upcoming and currently ongoing meetups, hackathons that's happening is DataStax ASTRA's Buildathon. It's already started since the beginning of this week, but there's 3 months and 3 rounds of challenges, one round of challenge per month. The top 3 winners for each round qualify to present their project ideas on demo day, which will be at the end on May 20th. And there's a bunch of prizes that you or your coworkers or your team can win in general. You can win per monthly challenge, but then you can also win for the demo day. And there's a bunch of other prizes you can win regarding engagement and swag as well. Anant is hiring. We are looking for full-time or part-time positions in the realm of data platform operators, engineers, and architects. If you are interested, you can find out more at careers.anant.us. Cassandra Lunch, this is a process, but this is just a reminder for everyone watching. Cassandra Lunches are now on Thursdays at same time, same place, but we are looking at changing the time slot up so it can be more available to everyone in the other parts of the world if they want to attend live. But again, we stream these live directly to YouTube. So if you aren't able to watch it live, you can watch it on our YouTube channel, youtube.com/AnantCorp, and you can keep up to date with the playlist as well. Upcoming events we have here at Anant, we have data engineers lunches, which happen on Mondays at noon Eastern currently, and then we have upcoming Cassandra lunches as well. You can find out more at our events page, anant.us/events. Again, as mentioned, you can keep up to date with all the Cassandra lunches that we've put together so far. We started recording around Cassandra lunch number 10. And so you can find from 10 all the way up until today on our YouTube channel, youtube.com/AnantCorp. Cassandra.Link should be your #1 resource for all things Cassandra. Cassandra.Link is populated and by hand-curated resources by the team here at Anant. And you can find out all the different resources from Cassandra or anything in the ecosystem like Cassandra, Spark, and Kafka. And if you have any questions or you want to learn about Cassandra, feel free to visit Cassandra.Link. And with that, we will go ahead and pass it over to our speaker for today, Rahul.
Hey, thanks, Markman. I appreciate it. It's a very amazing number, 88. It's like a lucky, 8 is a lucky number in the Chinese culture. And anyways, I like the fact that we've been doing this, what, almost 2 years. Maybe we've done it for 2 years. No, not quite, but we will come to that milestone. We got to celebrate. Yeah, so today, what I'm going to be talking about is, it's really new to me. I mean, the technology has been around for a little while, but I'd heard things about it, and it's only recently when I think Instacluster started to offer it as a managed service when I started to really pay more attention to it. So what we're going to talk about today is actually a little bit of a background, more theoretical knowledge about distributed transactions and workflows, and then how this technology, Cadence, can help people do that. And we'll talk a little bit about the background of why why Uber made Cadence. Uber is the company that made an open source Cadence, as well as there's another project called Temporal, which is a fork from Cadence, by the people that made Cadence at Uber. There's several source stories like that in the open source world. For example, right, Cassandra was made at Facebook. It became open source. The people that worked on Cassandra at Facebook, they made another database called Yugabyte. So both of those, Temporal and Cadence, are synonymous. They're not the same anymore. I mean, we're going to look at a few differences. But the important thing I'd like to get across today isn't, hey, this is a cool technology, but rather, why is it important to have a technology like this available to us? Most companies probably don't need to use something like Cadence. They can get away with a lot simpler workflows, and we'll discuss how DoorDash, Uber, both started off with simpler workflows, and then eventually had to end up using, Uber had to invent Cadence, and then DoorDash actually uses Cadence as well. So let me share my screen, and if you guys let me know, let me do this here. I'm going to share my screen from this monitor. Okay. All right, sharing my screen, let me know. Yes. Okay, good. Yeah, so today we're going to talk about Cadence temporal workflows. What is distributed transaction processing, and how to run those complex workflows at scale without reinventing the wheel. We have a mantra at our company: don't reinvent the wheel, which is like the story of all of open source. I feel like somebody doesn't like one open source project, they go make another one. But I'm giving credit to Cadence and Temporal because this is the first one that I've seen in a long time that is built on top of Cassandra first, and then they have adapters for SQL-like databases as well. There was another project called CassieQ, which was a queue processing, a queue storage and processing toolkit built on top of Cassandra. And some of those concepts I've actually seen in reading up on Cadence. But that project CassieQ isn't really managed, but it has some good concepts in there. Before we begin, we give a quick review of data pipelines. there's an overlap between distributed transactions and workflows and data pipelines, but we need to clarify what is what. And sometimes people refer to data pipelines when they're really talking about distributed transactions, and sometimes they're talking about distributed transactions when they're really talking about data pipelines. But data pipelines come in different ways, different purposes. They have different purposes. They're not created equal. They can all be done with different technologies. But here's a quick survey. So these are the different types of data processing, right? Data pipelines are used in data processing, but there are transaction processing, distributed processing, real-time processing, or stream processing, batch processing, and multi-processing. Transaction processing is and distributed processing is what we're going to talk about today. Real-time and batch, we've talked about other sessions at Cassandra Lunch or even on Data Engineers Lunch. And then multi-processing is simultaneous processing of any of these other processing types on the same data at the same time. There are different frameworks to help people do this. And from a pure data perspective, which is the movement and processing of data, there's a bunch of different frameworks out there. And I have not added Cadence or Temporal to this because when we go deeper into it, it's not a pure data processing framework. It's actually a software workflow framework. Then different workflow tools can be used on top of these or with these frameworks to do some of these different types of data processing. So if you're new to data engineering, or if you're new to Cassandra and data operations, data architecture, where do you spend your time? I would say you should understand the different types of data processing in terms of how to get data in, get data out of Cassandra, and maybe some of these tools that are not going to go anywhere, like Spark isn't going anywhere. Snowflake, BigQuery, Redshift, they're synonymous data warehousing technologies. They're not going anywhere. They work well with Cassandra because Cassandra is not a data warehouse. But in workflows, there's a lot of tools that come and go, and they're meant for different purposes. In another follow-up Data Engineers Lunch, maybe we'll go through each of these and how they're similar, how they're different. But Cadence and Temporal also don't fit in here because these are pure data workflow engines. All right, their goal is to produce data products, and with some light application engineering. So I would say like Cloudflow and Spring Cloud Dataflow, you can have some application engineering, maybe even in MuleSoft, maybe some in Airflow, and definitely some in Apache Camel. But I have yet to see in this gradient of technologies exactly where Cadence fits in. I think it's more similar to something like Camel and maybe a Spring Cloud Dataflow and Cloudflow than it is like, let's say, Apache Airflow. Transaction processing, and very specifically transactions, are things that either are done or not done, okay? So in a database, when we talk about a transaction, it means that, let's say some data was updated and it was committed and it's consistent across the whole database engine, right? In a business transaction, if many different tables need to be updated, certain databases, like let's say SQL Server, you can say begin transaction, end transaction. Either everything will happen completely or none of it will happen, meaning it will either write all those updates, or if something failed, it will do the rollback for that transaction. So transaction processing is really about how to do these type of business transactions and how to do it with consistency, because consistency is important. If you have an inventory and somebody's buying something from, through a shopping cart process and their order breaks, the inventory should be returned rather than be taken off, right? That means when the next person comes, they don't see it. The first person didn't get it delivered to them. The second person doesn't see it to be able to buy it, and then nobody got it, and the company lost money. So transaction processing is important in business because things have to be done or not done. You can't just have something in the middle. Eventual consistency is a way to do it, but strong consistency is needed in true business transactions. And we're going to talk about two different types of transaction processing methods. we're not going to go into distributed batch processing or real-time processing or how is distributed batch processing different than batch processing and multi-processing. But generally, these type of processing approaches really they work well with data processing, right? Like ingestion, transformation, like cleaning data or transformation with business logic, with lots and lots of information, where the criticality of when it happens isn't that important. It may be important to get a refresh every now and then, but it's not a complex workflow. Things are happening in a general order, and the data is eventually going to get updated. Same thing with machine learning. At least not yet, right? That the machine learning model that was trained does not have to be immediately available to everybody. And some systems are getting closer and closer to that. So when we talk about transaction processing, we're really talking about we're talking about applications at scale, right? But how do people go from their regular old, three-tier application, presentation, business logic, data logic, or N-tier application, or MVC, and how do they scale that? Right, MVC is a pattern, model view controller, or there's a model view presenter. All of these design patterns, they work pretty well in a monolithic software stack, and then you can break apart the different models, views, and controllers into different components. But eventually, large applications have to be re-engineered using the same patterns, but they have to be re-engineered in a different way. So let's look at what does real-time application look like at scale, what are the challenges and how to get there. And then we're going to go into what is transaction processing at scale, and then we'll take a look at Cadence. Hopefully, then you'll appreciate why something like Cadence is useful in the real world. So normally data applications, I would say majority of data applications that are started are CRUD apps. Not that they're cruddy as in they're bad, they're just create, read, update, delete. But some would say that CRUD apps are actually cruddy because they don't really scale. Essentially, the problem with these is that there's a database, or even if it's like Cassandra, the only thing the application is able to do is create, read, update, delete. But there may be other things that need to happen, and so either something is being done or it's not finished. It basically blocks processes. And we need some things to be blocked, some things should be open, but that's what we mean by synchronous, right? Things have to be done and then they have to finish before the next thing can happen. The databases, generally cannot handle tons and tons of transactions and tons and tons of reads until you get to a database like with Cassandra. But if there is complex business logic in the middle somewhere, right, there may be a point where data is coming in that is more current than the data that's being read. And that's the consistency problem that we have to think about. A very popular and common approach to...
I've got a question on that previous.
Can we wait? Can we put that in the question? Yeah, I'll answer it in the chat. Let me just finish my thought. The common approach for scaling from a pure CRUD app in the relational monolithic world is that relational databases, pure relational databases like MySQL, SQL Server, right? You cannot do millions and millions of create, read, updates, and deletes because of the locking problem, okay? So one way to manage that is, without using the CQRS model, is having masters or leaders and replicas. You have a leader that can do reads and writes, and you have replicas that just do read, they copy from the leader database, and then they basically allow systems to read. So you can do that by basically changing your logic to say, do all the create and deletes and updates all in the leader database, and do the reads all from the replica database, right? That's a first level of kind of separating the read and write traffic. But again, replicating a relational database to get to a very, very large scale means that if you're doing 1/10 of the traffic as writes and 9/10 of the traffic as reads, you need to have 10 types. You have to have 10 copies of that database. one is the leader and 9 replicas, because the data has to be completely copied, right? And that becomes inefficient. So what people started to do was they said, okay, let's break apart our application so that the queries are coming from one model and the updates are going to the system from another model. And it's okay for the command, which is the command model. It's okay for the creates, the updates, and the deletes to go to one database. And at the same time, we can do something to update another type of system for reading, which could be like a cache. So all the queries are coming from the cache rather than a full-fledged database. And that's kind of the starting point at where people start to use CQRS. And then later you could separate where the data is coming from, and you could separate different types of queries. So a search query comes from another database, or like an Elasticsearch index. An aggregate query comes from another place. A flat, data request comes from another place. And each of those independents could scale independently. And then we're really in the world of microservices where systems are built specifically for what they do. So let me take a look at this question. The question was, what does it mean by consequential logic? On slide 6, you said? Model execution, validation, and consequential logic. Consequential logic means is that it is doing the business, like if it's where they have, and we can read it up in the Martin Fowler article, but it's basically like if there is if then else type of statement, you can have that type of logic in there. If this is the case, then this is the consequence. If this is the case, then this is the consequence. That's where everything related to switch statements, conditions can be put in there. That's my understanding.
Great, thanks.
Okay, sure. And so even right here, if you notice, like the consequential logic comes in here, but in a read from the query perspective, there's no reason to have that. It's just doing a read, right? So we go from CRUD to CQRS. The next thing we can create to scale that even further is to introduce an event-driven architecture. Now, you don't have to have CQRS in an event-driven architecture, but CQRS can benefit from an event-driven architecture. And in event-driven architecture, what happens is that events are stored somewhere by publishing it to an event store. This could be a queue, it could be a database. And then subscribers pick off the event, they process it, and then they do something to different places. So why is this useful? Well, in CQRS, the command is an event. And in this case, it was updating the same database that it's pulling from, but we could update a database. We could put a file in the file system as a log. We could send an event to an API, get some data back, right? All of those things could be done from one event. And this can scale because you can have multiple events coming from multiple publishers. And you can have multiple subscribers and workers that are able to handle the scale of traffic. And they don't lock because it's a queue or it's a database that is just focused on doing writes and reads for independent. So there's a cost benefit of like, why would you use a database versus a queue? And Cadence is actually doing this inside Cassandra. The point here is that you're separating the scale by introducing this event store. The other benefit that we get from this is that if the system crashes, if we store the event data for all the commands, right, all of those commands can be replayed. The whole system can be rebuilt from the event data. This is also useful when we are trying to test out a new version of the software. If the event structure didn't change, we could change what the publisher does. We can change what the subscriber does, and we can even replace different databases in the back end here, and we can replay the event data to see, hey, does this system work well? And event data could be replayed at stress levels, meaning scale. So you could test out a system at scale before even going to production. Kafka gives us some of that ability. And the reason I mentioned Kafka is that people started to really buy into the Kafka ecosystem because it was offering people a place to do CQRS and event-driven applications, because people are just going to write data to Kafka, and then they will write their code to read from it and do stuff. And this is all good. It's all great. And we'll get to why this isn't good enough for some things. Why was Kafka created? Again, we should understand the background. Kafka was created because LinkedIn had a bunch of different databases and a bunch of different systems and a bunch of different events happening. And it was spaghetti code to make it update all the things consistently. So eventually they made a unified log of events. And all of the different systems were then updated using a subscriber from the unified log, right? So back to what is happening. We're basically taking all the events, storing them in an event store, and different processors for different databases were updating the different databases. And that allowed for a consistent enterprise. And as people started to use things like Kafka and stream processing, they realized that they needed both a speed layer and a batch layer. But this system still is all about data processing, pure data processing. It can do some business logic, but there's really no guarantees. There's no complex business logic. You can have some pipelines that just are going one way. And you can have DAGs, directed acyclic graphs. All that's good. And even the CAP architecture, which is all stream-based. Okay, all this is great. But where we fall short with this architecture in the application space is complex business logic. How to make sure things are done or not done. So between CQRS, Lambda architecture, CAP architecture, and what we're going to be looking at, people started to adopt microservices. Microservices is a loaded term. When people say microservices, I'm like, what are you talking about? Microservices for some people are REST APIs, some people it's GraphQL APIs, some people it's gRPC, right? General Remote Procedure Calls, and gRPC uses protobuf. For some people, a microservice could just literally be a database like Cassandra, where you read and write data. You know, in fact, Cassandra is built, I think, like as a set of like 16 microservices that move data around in events. So applications to scale need to go from this traditional single app process, or 3-tier, as I was mentioning, with a single monolithic database, to this UI that is maybe talking to separate services that have their own database. Okay, and these systems can scale independently. And let's say one microservice is becoming more popular. The stateless microservice can be scaled. The database that's backing it can be scaled. The other databases don't need to be scaled. Cassandra actually helps with the overall microservice architecture because it scales linearly. You can consider having tables backing different microservices on Cassandra and just have one infrastructure. And that's a paradigm shift for most people. People think, oh, microservice, single database. I'm like, no, Cassandra is like an infrastructure for data. So you can just have a billion microservices powered by Cassandra. There are several clients that I know that have 300, 700 node clusters that are powering 50, 60, 100 microservices that powers real-time enterprise. That's a different discussion. But having microservices doesn't solve the problem of how do these things get done or not done. The transaction, how is it done or not done? And this is the complexity that we're dealing with, right? We're dealing with having all of these single page apps, web components, native mobile applications, talking to API gateways, having all this stuff on containers, then talking to different databases in the background, in the data mesh, right? Going from here to here. So between our user interface and when the data comes in here, how do these microservices work together? Well, first, let's understand what type of microservice could there be. So there could be a REST API. We generally know what a REST API is, but it's a very common way to interact with a database. Most APIs are still REST APIs. Some of them are becoming GraphQL, which is still based on REST. Microservices at the core is a superset of REST services. And microservices, the idea is that they're loosely coupled with other services. They're independently deployable. They can be implemented in a synchronous or asynchronous method. So AMQP, Kafka allows us to do asynchronous microservices processing, whereas REST interfaces are synchronous. Each service can have its own database, quote unquote data store. In Cassandra world, we would have many databases or data key spaces or tables on the same infrastructure. But in a relational monolithic world, you kind of have to have separate ones for scale. The key thing here is that the consistency in the microservice world is achieved via SAGA pattern, two-phase commit, or eventual consistency. And we're going to talk about SAGA pattern and two-phase commit in a second, but eventual consistency is how Cassandra makes data consistent. Think about eventual consistency as when we are trying to save data to 5 places, we just look at the event log and we just keep trying until it's done. But there's no guarantee until you introduce things like SAGA pattern or two-phase commit. And back to event-driven architecture, how does it relate to microservices? It relates back to this diagram that events are published to the event store. The subscribers can take data off of the event store, and instead of directly talking to the database, they are then calling other microservices to do the operations. So the events could be in a database or a queue, right? Events are created via an API, and then the processors pick up the data and they process it and they update the application state, right? So in this case, the application adds an event to the queue. Kafka Streams is used as the processor. It reads from the event store, updates the application state, and could even simultaneously update the user interface. To close the loop on CQRS and microservices, CQRS we talked about is a way to separate command and query, right? Reads are separate from create, update, delete. Microservices could be used to do the commands. They could even be used to do the queries. So this back end here could be separated, right? Commands coming in here, coming from a database, queries coming from another player. The event processor basically is doing the storage of data in both, right? Update goes here, it goes here, and it goes here. Where do microservices come in? They come in sometimes here, and sometimes between the event processor and the actual database. That's a very simplistic way of looking at it, that all applications are basically a place to dump data and retrieve data. That's true, but there's some logic generally in the middle somewhere. So when we're looking at pipelines, usually in the data processing world, we have different patterns like a directed acyclic graph, okay? When we look at processing patterns inside transactions, I don't necessarily call it a pipeline. I would say it's a workflow. And this workflow is really right here. I know that Airflow does workflows. but it's basically managing the workflow of different things happening across time. And so in transaction processing, we're talking about the same thing, but in a much shorter time, or at least the scale is much smaller. We're talking about one customer ordering an Uber ride, and that one customer getting an Uber ride, and that one customer paying for the Uber ride, and then one customer getting bothered until they tip the driver, until they get the email saying, here's your receipt, right? That whole thing is a workflow. And it's happening for millions of users at the same time. It's not a data pipeline. It's a workflow. There are two types of distributed transactions that can guarantee consistency. One is called two-phase commit. There are many databases that are built on this premise, distributed databases. And then there's the SAGA method. And SAGA pattern can be done in two methods, choreography and orchestration. Two-phase commit is very simple to understand. It's complicated to implement. First phase is the coordinator goes to all the different, let's say, processes of the workflow of the transaction, creating the order, processing the payment, updating the inventory, delivering the order. It first asks all of these separate systems, are you ready or not? And after, and only after it gets an understanding that all these systems are ready, it then says, do the work. And then it waits for an acknowledgement. And if all of the systems send an acknowledgement saying, I've done the work, I've committed the work, then and only then does it say this whole thing is done. If any of them say, oh, I didn't get it, it says to all of them, roll back and try again. Looks simple enough. When you start adding more and more systems, this gets more complicated. The SAGA pattern, again, can be implemented in two ways, choreography or orchestration. One is messages are sent, they're relayed from one service to the other. And orchestration is when, again, it's very similar to the coordinator telling all these things what to do. But the orchestration engine itself is kind of keeping track of the whole thing rather than asking each system, are you ready to commit or not, commit or roll back? The orchestration is actually able to do the commits or rollbacks. Looking at two-phase commit in detail, it's a matter of like telling from the coordinator, prepare all these different participants. It's a vote request. It gets a vote saying, yes, I can do it. Here's a decision. And then all the participants say, I got it. There is benefit is that it's consistent and available. Data is always synchronized. There's a blocking protocol, right? Until all of these things are done, it can't do the next thing. And if you lose a participant, the whole thing doesn't work. If you lose a coordinator, the whole thing doesn't work. Framework for two-phase commit, there's a system called SAGA that can help people use two-phase commit to do this. There's a question in chat. Let's see. Is the problem of complexity with two-phase commit as you add more services to the limit of ESPs or complex systems, slide 23? So this is actually an idea of an ESP. It's partially that there's more systems more systems to basically do that process, right? The more you add, the more it has to do this process. It has to do this twice. I would think that would be the main thing. I think the complexity is one problem, but the fragility of it, I think, is the other reason that I think people don't use it unless they have to. Like in databases, people like to use this. Choreography pattern is where it's like we send events to a channel and a system picks it up, right, as an event, does something, and then it sends another event to another, queue or a channel, and another service picks it up, does something, so on and so forth, until the whole thing comes back to the order service saying, I got it, everything's done. It's great because for simple workflows, it just works. You don't really need to put too many things in place. If you have a system that has a task queue, it's kind of like using the choreography pattern. Drawback is that if you start to add more and more steps, your topology of your choreography gets complex, and it starts to look like a pipeline, but it's a choreography of things happening. And potentially what you can have is a cyclic dependency at which, it could cause an issue, I would say the testing of these systems is also very difficult. There are some patterns, there are some frameworks that you can use to use the SAGA pattern as choreography. Here's an example of choreography. Here's the coordinator. It sends messages. These things basically says, I'm starting the SAGA, and this thing is saying, I got this, I got this, I got this, I got this, I got this. And then we go from creating the order, processing, etc. At each of these steps, we have the ability to roll back if there's a problem. Okay. The orchestration pattern in the orchestration method or pattern in SAGA is where we have one coordinator basically getting everything done by other services, and it can use a message broker or a channel. It's just that it waits for things to get completed. So here's a command service, and here's a reply channel to say I got it, right? So everything is done through this chain of events where the one coordinator is getting everything done. It's great for complex workflows. When we need a lot of control, it's really good. Doesn't have cyclic dependencies, but it adds complexity to the design. And there's another point of failure, which is if the coordinator goes down, then something isn't going to work. There are different services, different frameworks available to use the orchestration pattern. There may be even more, but Apache Camel, which we saw earlier, can do this. Camunda, Activity, I think, can do this too. But the two that we're going to look at is Cadence and Temporal, because they use Cassandra, and this is a Cassandra Lunch. Here's another picture of the orchestration method in SAGA. Here we have one system basically saying, do this, come back, go to the next thing. If there's an issue, cancel the order. Go to the next thing, do this, come back. If something didn't happen, reverse the payment, cancel the order, right? So this code right here is the transaction that's making everything happen by calling these different services. How is this different from what we were looking at up here? It isn't. It's just the fact that the subscriber, or even this thing right here, or even this thing right here, the subscriber or the processor or the coordinator, it has to make sure these things get done. That's the difference in saying I'm using Kafka streams to do my workflow versus saying I have a SAGA pattern implemented as a workflow. Finally, punchline, Cadence on Cassandra. Cadence is a system that was built by Uber to handle complex workflows, essentially complex orchestration workflows for their business. Uber has to fulfill, let's say, an Uber Eats order, right? And it's got all these things that need to be done: placing the order, setting the dispatch time, telling the driver, hey, go pick it up, telling the customer, hey, here's when your food is coming. And until the whole thing is done, right, it doesn't say that the order eats over should charge the customer for that. And you can read more about it in the links that are going to be part of this presentation. But this very simplistic view of how Uber is doing, let's say, Uber Eats. They actually use it for lots of different parts of their business. How does Cadence work? There's Cassandra on the back end. It does not have to be Cassandra. It could be a SQL database like MySQL or Postgres. And so technically you could use Scylla or DataStax or ASTRA in the back end. You could use CockroachDB, which is Postgres compliant. You could use TIDB, which is MySQL compliant, and Cockroach and TIDB are scalable relational databases. So the Cadence service basically has the front end service, which allows workers to get access to the API to talk to it, but there's also a GUI. You can look at what's happening. The history service is basically what keeps track of what needs to happen. The matching service is what matches different workers or different activities to a particular workflow. And then the worker service basically runs the workers. Basically, it's actually in here, you can't see it, but it's basically telling these workers what to do. And the workers are where the business logic is executed. We can look at Cadence via a web UI. We can send commands via command line, or we can send API requests via HTTP. But it sits in front of Cassandra. The developer does not need to know what's happening in Cassandra. Now, the developer may have a workflow that is storing data in Cassandra. That's a different thing. You could have a system that's just using MySQL from an application perspective, but still use Cassandra for Cadence. Okay. The workflows have activities, and workflow can also call child workflows, which can also have their own activities. When I think in 2021, they shifted their architecture, they introduced gRPC as another way to call Cassandra. Call the Cadence service. Until then, they were using Thrift, and only Go and Java could be used with Thrift technology. Now, since gRPC is being used, we can have other applications that can use gRPC. So a .NET application, a PHP application, God forbid, Node, you can use gRPC to talk to Cadence. Here's an example. Let's say we start a workflow. The workflow starts, they can be separate workflows. So let's say I'm an Uber Eats customer. I order something, that's one workflow. Allison orders one, that's another workflow that's executed. And then each workflow can have multiple activities that are basically happening. My activity of delivery is separate from, let's say, Allison's activity of delivery. Here's a code example actually from Cadence's website. So let's say there's a subscription where we have a monthly cycle of billing the customer. Okay, and the workflow basically has manage subscription, which we'll take a look at, cancel subscription, update the billing period, charge amount, get the customer ID, query the billing period number, and query the billing period charge amount. So this is kind of the whole command, right? Here's your command and here's your query. And then in here, this thing is just going to run for one customer. It's going to run. If the billing period is 30 days, this will run. And when it gets to the billing period, it will charge the customer. Unless it's canceled, then it will cancel the transaction, right? And it'll increase the billing period number. And this thing will continue running. The cool part is, if the system crashes, because Cadence is storing the history of what's happening, the system can come back up and it can resume. That's where Cadence comes in. You can write this code in C++ or C# or Java or Go or Rust. Nobody cares. You can do it in PHP too. I hate on PHP. People use it. It's a joke nowadays more than anything. I really don't care if you use PHP. But the fact is that the resiliency of the whole workflow for multiple millions of customers who have, let's say, 10 activities each. So million times 10 million operations happening asynchronously and connecting different people. They could be asynchronous or synchronous. So like if I'm a driver for Uber and I get matched with a customer and the customer sends me a message, I should get that message pretty quickly, right? So that guarantee of getting the message can be managed with something like this. Some examples of people in the real world using Cadence that are not Uber. So Bonsai Cloud is a cloud company. And They have an offering called Pipeline, which is open source. And what they do with Pipeline is they allow users to create infrastructure and to run things all through Cadence. At first, I was skeptical. I was like, why would they do that? You could just use Terraform. And actually, if you read the whole article, they kind of replicate what Terraform does, right? But here's the catch. The reason it makes sense for them is that some customers need like 2 or 3 things. Other customers need like 50 different things. And rather than having to update a Terraform state and then run that Terraform state, what they do is they just say, customer asked for this, this needs to happen, let's go ahead and do it, let's make sure it happens. So it's an interesting use case to basically have real-time updates to infrastructure using Cadence. Now, the Cadence is open source, you can look it up, check it out. This is a screenshot of Cadence, like, hey, this activity took this long, this next thing is happening, right? Kind of like the console view in the web browser, you can see exactly how long things are taking. And this is just showing how, when they were writing it up, that they're storing the task, which is the matching service, the events from the history service, the workflow, and then visibility for the front end, right? Being able to see what's happening, how long things took. At Uber, they started with a very simple process that became a very complex process, where at each point in the microservices, they had a database and they're doing updates and blah, 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 right? And they realized they needed something better. So they created Cadence. And in this article, it talks about how they used Cadence to manage their ticket routing workflow. DoorDash has a service called Drive. It's like a delivery as a service. I guess it's similar to Grubhub in that respect. And initially, when they built the software, it was Python talking to Redis, and a Celery worker, Celery being the task queue in Python, was used to run processes. But as it became more and more, it became bigger and bigger, this wasn't cutting it. So what they did was they introduced Kafka to store the events, and then they used Cadence to execute the complex workflow. And you can read all about it. I'll leave that in the article, which will be posted. So we looked at a few different use cases. Let's talk about temporal. Temporal, as I mentioned earlier, is a technology made by the people that make Cadence. It's a fork from Cadence, so it's now actually wildly different. Temporal is a company also, whereas Cadence is just an open source project. Temporal allows users to use their cloud hosted service, or you can download and run it yourself. Cadence has native support for TypeScript and PHP. And they're basically selling the same Kool-Aid, right? Instead of using Redis and RabbitMQ or Kafka to do all of these different microservices, right? This complex workflow, it's telling you use Temporal to do all of these different things for you. Temporal will take care of the queue. It will take care of the storage of whatever you need to store in order to get all this thing done. And they have a lot of street credibility. Airbyte, which we have actually looked at before, Airbyte uses it. Datadog uses it. Datadog is a big company. Netflix is a big company. So if these folks can rely on Temporal, it validates 2 things. It validates the fact that Cadence used by Uber, DoorDash, okay, legit. And then it validates in a larger sense that the same core code base is being validated in use at these large companies. And that's really the nice thing about open source is when it clicks, smart people pick up on it and they start using it rather than either reinventing the wheel or building their own wheel, right? Just get with the program, just like use something that's available or pay somebody else to host it like Temporal. Temporal workflows, again, same thing as Cadence workflows. Ultimately, it's doing the same thing. There are a few differences, which I'll get to. Their UI look similar. They have a different logo, but mostly the same. And the main difference is there used to be a difference that Temporal used Protobuf and gRPC and Cadence didn't, but that's no longer the case. There are different names for these entities. Timeouts are different, retries are different. So there's a migration step to go from Cadence to Temporal. And that brings us to the end of our presentation. Hopefully this was useful to you. Goal here was for you to understand the value of workflows, distributed transactions, and complex workflows. And knowing that they're important at scale, seeing how Cassandra could be used with Cadence to empower your growing company or your existing company that needs something like this now. Thanks, everybody.
Alrighty. Thank you, Rahul. We are at time, so we will let everyone go. But if you're watching this on YouTube, don't forget to like and subscribe if you're not subscribed already. And also, please comment below if you want to have any topics discussed, either here on Cassandra Lunch, but also on Data Engineers Lunches. We are open to any suggestions, so drop it down below. If you want to be a guest speaker, you can reach out to me, urpan.patel@anant.us.